Yeah, now it is live.
Hmm. Can I sign out this Gmail? Sama Gmail.
Divya,
Yes, sir. Yes, sir.
Yeah. So can we start?
Yeah, yes, sir. Yeah.
Yeah, very good afternoon to good day to all the panelists as well as the participants of 8th lecture of meteorology, jointly organized by South Asian Meteorological Association and Birla Institute of Technology, MESRA. So now I request Professor Someshwar Das, Secretary of SAMA, to deliver the welcome address. Over to you, sir.
Thank you, Dr. Lakshmi Kumar, ABM, Dr. Pradeep K, President of SAMA, today's distinguished speaker, Dr. Pradeep Kumar Thapliyal, Scientist G and Head Geophysical Parameters Retrieval Division at the Space Application Center, ISRO, in Ahmedabad. He is also a member of the panel on Satellite Meteorology Committee of SAMA. Members of the organizing committee, distinguished participants from about 60 countries, ladies and gentlemen, we welcome you on behalf of the South Asian Meteorological Association and Birla Institute of Technology, MESRA, India. By today, well, now that the registration is closed, but whatever people have registered so far, I can see there are 1,805 candidates registered for this course. The lectures are also becoming popular on the YouTube as the number of hits are increasing day by day. The inaugural lecture of this series has been viewed by more than 2,000 people, that is about 2,351 people, while the last lecture has been viewed by 231 people. And these numbers, as you know, are increasing day by day. Well, to summarize this lecture series, we have already done it in the past, but I can just quickly summarize once again. As you know, this is the 8th lecture of the 20 lecture series on satellite meteorology. This is a continuation of our efforts on capacity building of the people of this region. Many of you may know that we conducted the first online lecture series on atmospheric physics jointly with the SRM Institute of Science and Technology, Chennai, for 4 months during January to April 2023 this year, in which more than 2,000 people from 48 countries registered for the course. We conducted the second online training on the WRF modeling system jointly with CDAC, that is the Center for Development of Advanced Computing in Pune, India, during 3rd to 24th April 2023, with hands-on training on the supercomputer of CDAC by remotely logging from different countries of SAMA. This is the third attempt, as I said, on capacity building of people in satellite meteorology. We have a distinguished panel of very senior scientists and professors from reputed institutions of this region who are experts in this field. The syllabus of the lecture series has been designed based on the feedback and requirements of the member countries of SAMA. This lecture series is targeted to postgraduate students and professionals of non-meteorological background who are interested in learning the subject of satellite meteorology. This lecture series will continue for 5 months, started on 2nd of September, and will go on till 20th of January 2024. As it was announced earlier, we shall provide certificates to the participants who will have at least 75% attendance. Those interested in receiving grade certificates, that is outstanding, excellent, very good, good, etc., will have to appear in a evaluation test which will be conducted at the end of the lectures. The lectures, as you know, are live streamed on the YouTube channel of SAMA. They will also be available afterwards on the YouTube for those who could not attend the course live. We shall try to have more interactions between the speakers and the participants in this lecture series. So please write your questions in the chat box, and our moderators will pick up the questions at the end of the lecture, and they will be answered by the speaker. So enjoy the lectures and have a good time. Wish you all the best. So on to you, Dr. Lakshmi Kumar.
Thank you, sir, for delivering the welcome address and also welcoming the participants as well as the panelists. So now I request Dr. Ajit Tyagi, sir, President, South Asian Meteorological Association, to deliver his address to the participants. Over to you, sir.
Thank you, Lakshmi, and very good afternoon to all participants. Dr. Thapliyal, I think he is well-known personality as far as South Asia is concerned, but for the other participants also, he is one of the leading operational scientists in the satellite meteorology, who is converting the various sensors data to the operational applications. So thank you, Dr. Thapliyal, you being the one of the key member in planning this particular training on satellite meteorology and suggesting the speakers, the topics, and yourself, you are taking the lecture. So welcome and thanks a lot. Dr. Somesh, Professor Someshwar Das, who is, I think, the key person in organizing all these training programs, and our organizing committee from BIT, led by Swagata, Divya, and other colleagues. And of course, we have Dr. Mohan Das and Akhilesh joining after a long time. So welcome, Akhilesh. This series of lecture on satellite meteorology, as I mentioned, had been planned very well, starting from the basics of remote sensing to the advanced sensing and how the various these sensors, maybe the multispectral, are being used in operational setup. Dr. Thapliyal, I think, needs no introduction, which formally will be introduced, but from India Met Department, we had been following his work and his various awards as the research as the best research papers in by the IMS, by ISRO, are well known. So, and he'll be talking about very important aspects of remote sensing and how those products are being used in our applications. So make best use of it. As I had been mentioning in my earlier addresses also, this is an opportunity. This is a platform where not only during the lecture, but thereafter also, if you need some more guidance, we request all our mentors and the speakers to support and guide. So please make full use of this lecture by seeking any clarifications or explanation you want, and thereafter also use this platform to develop expertise in satellite meteorology. As mentioned, we have these lectures available on YouTube, so you can go through again, and you are welcome to participate in the so-called evaluation process to receive certificate from SAMA, which is, I'm sure, will be of good use in your CV. So have a good time, enjoy your lecture, and make best use of it. Thank you.
Thank you, Ajit Tyagi, sir, for addressing the participants. Now it is lecture time. So before going to the lecture, I requested Dr. Akhilesh Mishra, Scientist, National Center for Medium Range Weather Forecasting, and also Executive Coordination Team member of South Asian Meteorological Association, to introduce today's speaker, Dr. Pradeep Thapliyal, sir. Over to you, Akhilesh.
Thank you, Dr. Lakshmi. It is indeed a pleasure and honor to introduce such a highly rated speaker. As President Sama already introduced and informed that Dr. Thapliyal needs no introduction. Younger audience and students from across the countries, different countries, I would like to read briefly what Dr. Thapliyal is all about. Dr. Thapliyal is Scientist and Head of the Geophysical Parameter Retrieval Division of SAC ISRO Ahmedabad. He is currently working in the field of satellite meteorology at Space Application Center since 1995. And Thapliyal has major contribution in the development of operational algorithm for retrieval of various geophysical parameters from Indian as well as international satellite missions, such as atmospheric temperature and humidity profiles, upper tropospheric humidity, outgoing long wave radiation, sea surface temperature, ocean surface, short wave radiation, clear sky radiances, and soil moisture. Several awards and honors are there in his bounty, and he's been awarded ISRO ASI Award in 2015, PRP Shorty Memorial Award by ISRS in 2012, IMS Award for Best Paper Published in Atmospheric Observation and Technologies for 2011-12 and 2019-20. IMS Award for the Best Paper Published on Weather and Climate Services for 2020-21. ISRO Team Excellence Award for 2008 and 2013. Is actually MSc in Physics from HNB Garhwal University in 1990. PhD from IISc Bangalore in 2004. Several achievements are there in his name. During 2005-06, he was visiting scientist University of Wisconsin, USA, where he worked on the development of the algorithm for hyperspectral sounder. He was also a very, very key player in the development of the MMDRPS system, which is for INSAT 3D series of satellite that is now operational at IMD New Delhi. Presently, he is also working as the Associate Project Director for OceanSat 3, US 6, also known as US 6 Science and Applications. He's the ISRO nominated member for various international science groups and such as DSICS and GHRSST, which is recently mentioned. He was busy with organizing the conference and SSTVC. He has more than 50 papers published in peer-reviewed international journals and has served as an associate editor in the Journal of Earth System Sciences during 2012-16. Dr. Thapliyal and I shared some personal relation as well. I studied in the same school where he studied in a primary school in Joshimath. His younger brother was my classmate. But what is most important is professionally he's doing very, very important work in the area of we are all getting benefited, especially in the numerical weather prediction community. The three main components are basically satellite meteorology, data assimilation, model development, and HPC. And the work done by Dr. Thapliyal is enormous, and his contributions, his support for Ministry of Earth Sciences, his support for National Center for Medium Range Weather Forecasting and other weather communities are huge. And with those words, I can continue praising him, but with those words and keeping the time in mind, I would now like to request Dr. Thapliyal to take over. Lakshmi, please. Thank you.
Yeah, thank you, Akhilesh. So now I request Thapliyal sir to proceed for his talk.
Thank you very much for his nice introduction. Okay, so I'll start sharing my screen now.
Yes, sir, please.
Can you see my screen?
Yes, sir. Yes, sir.
Okay.
Yes, it's perfect. Yeah.
Okay, I'd just like to.
I request participants to type your questions in question and answers box. So later the moderators of question and answer session, they will take your questions. Sir, please, sir, you can proceed.
Okay. So good afternoon, respected Dr. Tyagi, Dr. Das, other panelists, attendees in this Zoom meeting, as well as attendees who are attending from YouTube channels. I'll be talking about this brief theoretical aspects of atmospheric IR and microwave sounding products from satellite, products available and their applications with a special emphasis on state-of-art hyperspectral sounding. So as previous lectures, you must have. So many things have been covered in previous lectures, so I would like to skip those quickly. And in fact, last lecture by Dr. Radir, he has also covered a little bit of sounding. So I think that will become this task a little easier to understand during this lecture. So basic role of satellite for applications. How to... I'm seeing this bar on top.
Sir?
I'm seeing a bar on this top. How to remove that?
I think you can hide it, sir. There is some hide option, is there?
And it's
But we are not seeing that bar. You can continue. We are not seeing that bar.
okay. You're not seeing that, no?
No,
Okay.
no, no.
No. For him, I think it is obstructing his text, I think.
Fine, yeah.
You can drag it to down otherwise. You can try, sir. Maybe that is obstructing your text, I think, for you.
Yeah, that's right. This one. Not really. Anyway, I'll continue. That's only hiding the top part.
Yeah,
okay,
yeah.
so the satellite, sensors are very, very important for monitoring weather events. You know that the cyclone type of events, which originates over oceanic region, they are very difficult to be observed by any of the instrument based on land. But if you have satellite can keep an eye since the start of this cyclone, since the beginning of the cyclogenesis. For cyclogenesis, various atmospheric parameters are important that can impart various information, whether the area is likely to develop into a low pressure, then followed by cyclone. And then once it's developed, other instrument like imager can keep on tracking the system and where it is moving, that can be monitored and predicted. So the monitoring of this weather events, so meteorological processes are all very that they are global in nature. So before satellite era, only they were monitored through the ground-based instruments, and now you have satellites which can see through the entire globe, either ocean or land or polar region, with equal efficiency. So operational weather forecast, they are now casting, that is forecasting for very next few hours. Short range for 1 to 2 days, medium range for few days to weeks, extended range that is about a week to month, and then there is seasonal prediction. So most of these phenomena, they require data or the condition, atmospheric condition, as well as oceanic conditions to do monitoring and prediction. So most importantly, the meteorological charts, they are surface pressure, temperature, humidity, wind speed, and direction. So they are traditionally surface observations. There are surface met observatories which can measure these parameters, and they are through GTS they are transmitted to various these meteorological agencies worldwide, and then meteorological charts can be prepared with the simultaneous observations of these parameters, and meteorologists can make inference on this weather or atmospheric state during next few hours. Then when you are talking about local weather, like over Delhi or over Ahmedabad or any other place, so for that shorter time scale is actually influenced by regional atmospheric state. Maybe the atmosphere which is vicinity of that area, about 500 to 1,000 kilometers, will be important for next few hours. So what you say, that data requirement will be regional. Only around that region, the data is important for you. But if you are talking about local or regional weather at longer time scale, for example, few days to a week, then in that case, the weather event over a particular area can be influenced by global atmospheric state. So the data requirement becomes global, and it's not only surface, but the requirement becomes three-dimensional. You can see here, if you divide entire Earth into grids of equal size, equal cells, maybe 50 by 50 kilometer or 10 by 10 kilometer, and then also you divide in atmospheric layer into 50 layers or 100 layers. So you require those data over at each grid cells, at every cube location in the globe. So the NWP requirement, the three-dimensional atmospheric state as initial conditions as defined by these grids. And those grids are defined by your requirement. If you are going for global and long-range prediction, then horizontal scale can be 10 to 100 kilometer, and you can have around 50 vertical layers. That is, example are ECM developed, NCEP or NCEMA developed models. Now, if you want to have a local or regional prediction, shorter range prediction, then your horizontal scale has to be a few kilometers, 1 kilometer to 5 kilometer, and then you need to have very thin vertical layers in atmosphere. So about more than 100 vertical layers are required. So that defines the requirement of data globally. So, for example, if you see that what are the data which you require for this weather prediction, so this is a list of some of the parameters. They are not all, but Atmosphere, you need temperature sounding, water vapor sounding, trace gases, winds, cloud, aerosol, earth radiation, buzzard, precipitation, ozone, and then there are various parameters over ocean and land. Now, out of these parameters, some of the parameters can be derived only through atmospheric sounder. For example, temperature sounding, water vapor sounding, trace gas sounding, they can be acquired only through atmospheric sounder. And there are other parameters also that your sounder can make measurements, like cloud properties, aerosol, ozone or ozone profile, surface temperature, as well as various other land characteristics such as emissivity. So sounder can provide you information on many of these parameters, and rest of the parameters can be obtained through imager or radar or some other satellite instrument. So I'll be talking only about sounder, particularly the hyperspectral sounder. Now, I will also just a brief introduction only I will give about this remote sensing. So, the primary source of energy on our Earth atmospheric system is sun. So, Earth and atmosphere receives solar radiation primarily from 0.4 to 0.8 micrometer, that is visible region. And Earth being, this transparent in this window, that most of the radiation reaches Earth's surface. Some of that gets absorbed by atmosphere, and then the absorbed part, Earth becomes heated up, and Earth also starts emitting. So now Earth is emitting at a black body temperature of around 300 K. Okay, and then it starts emitting, but because the dominant part of radiation from Earth and atmosphere is in infrared region, the peak is around 10 to 12 micrometer. So that there are many gases, various gases in atmosphere which absorb infrared radiation. Primary of that gas is water vapor. Then there is carbon dioxide and methane and various other gases which absorb infrared radiation. And then the atmosphere absorbs and also get heated, because atmosphere is absorbing infrared radiation. So by way of absorption, this atmosphere also gets heated up, and then remaining part goes out of atmosphere that we call as outgoing long wave radiation. In between, apart from gases, there are various other atmospheric phenomena that interacts with the electromagnetic radiation. For example, clouds. Cloud is strongly absorb infrared radiation and strongly reflect visible radiation. So that becomes very, very important for studying remote sensing. So in infrared, whenever there is a cloud, so cloud, it absorbs all the radiation which is going from Earth's surface and atmosphere, and because it has absorbed entire radiation, it will emit only radiation which is emitted from cloud top surface, and that radiation will be at a physical temperature which is the temperature of cloud top. That is it will be around 250 if it is middle level cloud. If it will be around 200 Kelvin if it is a high level cloud. So depending upon this height of cloud, the radiation will be affected. Now there are various other processes like scattering by water vapor or various gases and this raindrops. That also takes place. So basically there are two types of sensors: active sensor and passive sensor. Passive sensor, where the satellite instrument is only measuring the energy which is radiated by Earth's surface and its atmosphere, or reflected the radiation which is coming from sun, but it is getting reflected by Earth, atmosphere or cloud surface, and then it is received by satellite. So satellite itself is not the source of energy for that in that electromagnetic part. So that we call as passive remote sensing. For example, of all our imager or sounder, they come in the category of passive instruments. Then there is another category, that is active sensor. So active sensors are, that the instrument itself is a source of electromagnetic energy. So energy is, it's emitted from, or it is sent from instrument towards Earth and atmosphere, and then it measures backscattered or reflected radiation from Earth atmosphere or Earth surface. So the example are a scatterometer, altimeter, GPS RO, LiDAR, and so on. So we will be here, because this is atmospheric sounding, so we will be mostly talking about passive remote sensing. Now, because there are many slides and most of them are common nature, so I will quickly skip those, because otherwise we have to finish in, I think, in 45-50 minutes, so that we have enough time for questions. So before going to atmospheric sounding principle, I just want to give this summary here, that Because how do we make atmospheric sounding from electromagnetic spectra? We have to know that what are the processes that are absorbing and emitting, what are those gases which are absorbing radiation in atmosphere, and at what wavelength or frequencies. Okay, for example, if your energy of radiation is very, very high, like in ultraviolet or X-ray, in that time the atom or the molecules in the atmosphere, they can get ionized, or there can be dissociation. Oxygen can break up into two oxygen atoms. So that process is called ionization, dissociation. But that happens only when energy of electromagnetic energy is very, very high, or that is the wavelength is less than, say, you can say 0.2 or 0.1 micrometer. Now there is another interaction that is electronic transition. What happens here? And there is an atom where electrons are rotating in its various energy states, various orbits. So energy, if it absorbs energy of certain this amount or certain wavelength, it can jump into the higher orbit by absorbing that radiation. And opposite, if it emits the radiation, it can come back to the lower energy state in the atom. So this happens only in the ultraviolet and visible region of spectra, where atmospheric gases can absorb and emit energy by jumping from inner to outer orbit in an atom. Now, the next very important energy interaction is vibrational transition. You know the molecular structure? Molecules can have vibration. Okay, so those change in vibrational state of energy occurs when the molecule, now it is not atom, this is molecular spectroscopy. When molecule absorbs energy at certain wavelength, wavelength, it can change the level of vibration, and by changing the vibrational energy states, it can absorb or emit the radiation, and that occurs in the infrared region of the spectrum. Then finally, when energy is very, very low, that is the wavelength is very, very high, in that case, the rotation transition can happen where molecules are free to rotate in different rotational energy states. So this is all about spectroscopy, and this happens for many gases. There are many gases in the atmosphere which have this type of absorption and emission. Primarily, the carbon monoxide, carbon dioxide, nitrous oxide, water vapor, then ozone, methane. Okay, and there are certain gases which will not have any emission and or absorption due to vibration and rotational transition. So we will only focus on those gases which are absorbing and emitting radiation in the atmosphere. Now, this is one very interesting diagram you can see here. If you see the electromagnetic spectra from 0.2 to 70 micrometer, you will understand that this left side is actually solar the radiation. So now at sun, at the top of atmosphere, Earth's atmosphere, if you have a spectrometer, your spectra will be something like this solid line here. This is a typical Planck black body function. Okay, but when you make the measurement at Earth's surface, when you are measuring that solar spectra at the Earth's surface, you will find spectra something like this. Okay, this is the solid curve here. And why this is happening? Because all the radiation which is there in lower wavelength side in the ultraviolet region, that gets absorbed by ozone in that stratosphere, ozone and oxygen in the stratosphere, and that is why we are not able to receive that radiation at the Earth's surface. Now, when you move here further, up to here, it is only absorption by oxygen, ozone, or scattering by different gases, Rayleigh scattering by gases. So this is scattering part here, and this is absorption by oxygen and ozone. So this part is absorption as well as scattering by atmospheric oxygen and ozone. Now, when we move further, here Rayleigh scattering is not significant, but then there are various energy, there are various absorption lines, absorption bands there, and those absorption lines are mostly because of water vapor. You can see here, this is water vapor. You can see there are various absorption bands around 1.9 micrometer, 1.34 micrometer, 1.5 micrometer, 2 micrometer, 3 micrometer, and then there is a very big absorption band around 6 to 8 micrometer here, and beyond that, then there is continuum absorption by water vapor. So we have to keep these absorption bands in mind when we are talking about, or when we are studying atmospheric sounding. Another important gas here is carbon dioxide. Now, carbon dioxide will have absorption band only around 2 micrometer, then 3 micrometer, and then around 4 micrometer, and then very strong absorption band around 12 to 15 micrometer with peak at 15 micrometer. Okay, so these carbon dioxide and water vapor absorption bands are very important for understanding the atmospheric sounding. And you can see here, if we are measuring this radiation which is emitted by Earth's surface, suppose Earth's surface is at 310 K, that is this line here, okay, and then this is a cloud surface. The cloud, top is at 210 K, so the black body spectra will be something like this blue line. Now, when we are measuring that radiation by keeping your instrument or sounder at the top of atmosphere, you will be not be will be measuring the function something like this black body curve, but the spectra which you will be measuring will be something like this. That at the top of atmosphere, you are receiving very less energy, between 6 to 7 or 8 micrometer, because of absorption of water vapor. And then there is atmospheric window, this region, that entire radiation which is emitted by Earth's surface is able to reach top of atmosphere. Okay, that is we call as atmospheric window. But within those atmospheric window also, you will find some of the absorption band. For example, one prominent absorption band is here, this around 9.8 micrometer, and this is actually the ozone absorption band that you can see here. Okay, so at 9.8 of the ozone absorption band is also seen here. Then again 10 to 12 there is no absorption, but there are various lines, various line features here, and those absorption lines are basically because of water vapor absorption lines you can see here. Okay, and then beyond 12 micrometer again, then there is a dip at top of atmosphere. Radiation is not received at top of atmosphere because of strong absorption of radiation by carbon dioxide gas. So you can see here carbon dioxide, it has a strong absorption band from 12 to 15 micrometer with peak at 15 micrometer. Okay, so this type of absorption feature we will be making use of studying atmospheric temperature and humidity or other trace gas profiles. So for example, if you go here, you will see that typically there are two spectral region where we do atmospheric sounding. First important part is the infrared. So you can see from 4 to 15 or 16 micrometer. This part you have predominantly three absorbing gases: water vapor, ozone, and carbon dioxide. And there are various other absorbing gases also, like methane here, CO will be here, and nitrous oxide. But let us focus only on three, the primary gases, for which we will try to understand how we will do sounding of these gases or temperature. Okay. Then the right part shows microwave. Now, when we are talking about sounding in microwave region, then the important the spectral regions are around 22 gigahertz, that is absorption by water vapor. Then there is another spectral region 50 to 60 gigahertz, that is a strong absorption by oxygen gas. And then there is another this sharp absorption band at 120 gigahertz by water vapor. And then there is a broad spectral absorption band that is due to water vapor around 183 gigahertz. So these absorption bands in microwave and these absorption band left side in infrared, they are used for atmospheric sounding. Basic principle remains same. Okay, but the only thing will be the radio transfer model. This modeling will be different in these two spectral regions. Now, a little bit of the absorption and emission in the atmosphere. Suppose I ask you to measure temperature of a surface. What you will do, basically, you must have seen that to measure temperature, forehead temperature these days, or to measure the fever, degree of fever a person is having, you also must have seen that there is an IR gun. Okay, doctor will place it near to your forehead, and then it will measure what is the temperature of your forehead. That is because you have a radiometer that is working in infrared window, that is around 10 to 12 micrometer, and that radiance which is received by, which is recorded by your instrument, is converted into brightest temperature or temperature of your forehead. Now, similar thing we can do if a satellite instrument is measuring your radiation, emitted radiation of Earth's surface between 10 to 12 micrometer, because there is no absorption by atmospheric by atmosphere in between. The radiation which is emitted by Earth's surface basically will be reaching your satellite instrument. So it means if we invert that radiation by using inverse Planck function, you will be able to measure what is the temperature of Earth's surface, okay? Or if there is cloud, suppose it's not surface, but if there is opaque cloud, so then that radiation which is emitted by cloud top temperature, basically that is recorded by satellite instrument in 10 to 12 or atmospheric window region. And if you invert that using inverse Planck function, you will be getting basically cloud top temperature, okay? Of course, it's not completely transparent. There are little absorption by water vapor or some other gases in between. So you'll have to do correction for that. But now that is measuring temperature of a surface, or either Earth surface or sea surface temperature or cloud top. But how to measure temperature of atmospheric layer? So your satellite instrument should be able to measure any radiation which is emitted by different atmospheric layers. Okay, if you have the ability to measure the radiation which is emitted by different layers, like that is there at 1 kilometer height, 2 kilometer height, 3 kilometer height, and so on, you may be able to invert that and try to get the temperature of different atmospheric layer. So how do we do that? So we will try to make a measurement of radiation in an absorption band of a gas where level of absorption strength is different. So I'm not going into much detail of this. You know that the radiation which is received at top of atmosphere is provided by this I lambda, and that is a function. There are various terms here. The first term is actually the radiation which is emitted by Earth surface. Okay, this one, Earth surface, and that is Planck function. Planck function, that is the temperature of surface, and from that you can derive that you can compute what is the radiation emitted by Earth surface at a particular temperature, frequency or wavelength nu or lambda. Okay, then you have to multiply that emissivity, because how much radiation is emitted by Earth surface, because it is not a perfect black body. And finally, you have to again multiply by tau, that is transmittance from surface to top of atmosphere. So this first term tells you that how much radiation has emitted from Earth's surface, that is recorded by satellite instrument. Then you have to add another part, that is the second part here. The second part tells you how much, then there are various layers. If you divide this atmosphere into various layers, say 100 layers in atmosphere, each layer is emitting, and then that is being recorded by satellite instrument. And if you add that, that becomes the second component. And so that we are writing here in integral form from surface to top of atmosphere. So this first term B lambda is this Planck function for each atmospheric layer, and the temperature of that layer is given by Tp. Multiply by, so how much is the function, how much is the contribution of that layer to the satellite instrument measurement? So then there is a multiplication by a weighting function del tau by del P. This tau is transmittance from that layer, that particular layer, to top of atmosphere. Okay, so this second term is contribution of radiation which is emitted by various layers in atmosphere, and that is recorded by satellite instrument. Third instrument is, I'll just briefly describe this, but later on to explain what is sounding, I'll drop this term. Third term is the reflection term, because if atmospheric layer is emitting, it is emitting in satellite, direction of satellite, as well as a direction of Earth surface. So the radiation which is emitted downward towards Earth surface, that also gets reflected by Earth surface, and again it reaches satellite instrument. So that additional component which is emitted by atmosphere and travels towards Earth surface, and then again gets reflected to towards satellite instrument, is given by this third term. So here this first term is albedo or reflectance of Earth surface. This tau is transmittance from Earth surface to top of atmosphere. And then again, this is integration term, that because we have to integrate the reflected part from each of the atmospheric layer. So now, because in infrared, Earth's emissivity is almost 0.98, 0.99. We can consider in infrared that Earth is around almost a black body. So the first reflectance term becomes almost very equal to 0, very small term. So this last term we can drop in a radiative transfer model for atmospheric sounding in infrared. So what will happen? You only have two terms, that is the contribution from Earth surface, and the second term is contribution from atmosphere. So now in next one, I explain by the figure, you will be able to understand that how we can interpret that. The second term is emissivity. So this emissivity term is also very important in atmospheric sounding, because if Earth's surface is being viewed, then this emissivity becomes very, very important, okay, because that tells you how much is the emission from the surface cloud or Earth or water or what type of surface it is. So that spectral emissivity knowledge should be there. So you can see these are the curves, these are the spectral library for different type of surfaces, for clear water, turbid water, wet soil, dry soil, vegetation, snow, and so on. So this is the spectral region in nanometer, and then this is the reflectance, or you can convert this into emissivity. This is spectral emissivity in infrared, and this one is spectral emissivity in microwave. So those all these informations we already have from our spectral library of emissivity, so that can be used directly in your radiation transfer models. Now, because you see that traditionally your atmospheric sounding is done by launching a radio sonde, or now you can say GPS sonde, because a gas-filled balloon, a light balloon is lifted from various surface observatories, and at the bottom of that you have tied one instrument that records temperature, humidity, wind, or other parameters when that balloon is lifted in atmosphere. So various atmospheric layers, the information is recorded by the instrument and then transmitted back to your surface instrument, okay, the transmitter. Now you can see that if you rely only on those radio sound networks, there are very few places where over entire globe where you can get atmospheric sounding. So three-dimensional information of temperature and water vapor is very difficult to get if you rely only on surface-based radio sound observations. And over oceans, you can see there are negligible amount of observations available. So if you want to do the prediction, the information over ocean also is very important, and that is missing from your ground network of radio sonde. But if you have satellite-based sounding systems from polar orbiting satellite as well as geostationary satellite, you can cover entire globe completely and with very high repeatability. These radio sonde, they are launched only twice daily by Met observatories over different observatories in the world. That is at 0 GMT and 12 GMT, and that is done to make in order to make a synoptic view of atmospheric state, and then that is input for this numerical prediction models. Now, these satellites can provide you very frequently. Geostationary satellite can provide you information every half an hour to 1 hour frequency, whereas the polar orbiting satellite can provide 2 observations per day, one during ascending and one during descending orbit. But if you have more than 3-4 satellites, so you can get sounding, or you can get the sounding of a particular region covered every 6 hours, or even at 3 hours if you increase the network of satellites. Now, anyway, this I have briefly described there, that if you have a sounder, and that sounder is measuring energy in different spectral bands. If I take a atmospheric sounder from 4 micrometer to 15 micrometer or 16 micrometer, and the radiation, you are measuring radiation at different wavelength region here. So what will happen? You will be basically measuring the part of water vapor absorption, the part of ozone absorption, and the part of carbon dioxide absorption. Now, first important thing is, if you want to measure temperature profile of atmosphere, you have to be making measurement in an electromagnetic part of a spectra, where the gas which is absorbing should have a known concentration and well-mixed gas. It should be a well-mixed gas having a known concentration, and a good amount of absorption should be there. So one such gas for temperature sounding is carbon dioxide. You know very well that carbon dioxide gas is well mixed throughout the globe, and throughout the atmosphere, the mixing ratio remains fairly constant, that these days around 420-430 ppm. So that because we know that what is amount of carbon dioxide in atmosphere, okay. So if you see this radiation transfer equation, what will happen? If you are making measurement in this part, suppose 5-6 channels in this part here, then in the radiation transfer equation, the only unknown quantity will be vertical temperature of the atmosphere, because the weighting function delta by del P is a known quantity, because you know the concentration of carbon dioxide in the atmosphere. Okay, so when you are making 5, 6 or thousands of measurement in carbon dioxide absorption band. So you are measuring the radiation emitted from various layers in the atmosphere. Now, when you make observation in water vapor absorption band here, in this case, there are two unknowns in this equation. The first unknown is temperature, because you do not know temperature profile in the atmosphere. So this T at different layer is unknown. At the same time, this del tau by del P, that is weighting function, that also is unknown, because this weighting function also depends upon the concentration of water vapor in the atmosphere. And concentration of water vapor, you know very well, this is very highly variable in space and time. It changes rapidly. It can have any large amount over near surface and very low amount above atmosphere, in the middle atmosphere. And sometimes it can be opposite. The lower atmosphere may be dry and higher atmosphere may have higher water vapor amount. Okay, so that becomes a little difficult to make sounding here, but then I will describe how we do that. Now, let us focus on two of the absorption bands. One is CO2 absorption band, and there is water vapor absorption band, where we will try to understand how we are doing atmospheric sounding. So let us first take the CO2 absorption band. We will say that this is 15 micrometer here, and this part, this is 12 micrometer. So 12 micrometer, you know, that is atmospheric window. Here, the absorption by CO2 or atmospheric gases is very, very small. So whatever radiation is emitted by Earth's surface, that entire radiation it will reach satellite. Okay. Now, when there is no absorption by intervening atmosphere, within atmosphere there is no absorption. So, you know, if there is no absorption, there will be no emission also. So at this wavelength, that is lambda 1 or around 12 micrometer, the entire radiation which is received by satellite instrument is from Earth's surface or near surface layers. There is very negligible amount of contribution from atmospheric gases. And in this, at this wavelength, the gas which is absorbing in atmosphere is CO2, and the absorption strength is very, very small. So you can say that the satellite instrument is not able to see the atmosphere, it is only able to see the surface. Okay. Now, if you convert that into a weighting function, the weighting function for this lambda 1 will be something like this. That the maximum contribution is coming from surface, and very little contribution is reaching from lower atmosphere, and upper atmosphere there is no contribution. It means if a temperature at middle level or upper level is changing by even 10K or 20K or 30K, there will be no change in the radiance which is or reading which is received by satellite radiometer. Okay, at this lambda 1. Now I will directly move to the contrasting wavelength, that is lambda 3, that is at the center of absorption band, that is around 15 micrometer. At this wavelength, there is a very strong absorption by CO2 in the atmosphere. So what will happen? Whatever gas, the third part I'll move here, whatever radiation is emitted by Earth's surface, that immediately gets absorbed within 1 or 2 kilometers in the atmosphere. It means the radiation from Earth's surface or lower atmosphere is not able to reach satellite. So satellite cannot see surface or lower atmosphere at this lambda 3, at this wavelength, that is 15 micrometer. But if you go up and up, even middle, the absorption strength is so high that even the radiation which is emitted by middle atmosphere is not able to reach satellite. So satellite is measuring only radiation which is emitted by upper atmosphere, that is around stratosphere. Only the radiation which is emitted from stratosphere or upper atmosphere is able to reach satellite, because beyond that layer, you know, there are the gas concentration for CO2 will be very, very small. So very small absorption. So satellite will be able to see the radiation which is emitted by upper atmosphere at wavelength lambda 3. So weighting function will be something like this, that the satellite radiometer or sounder is sensitive maximum to this layer, this level here, that if there is a change in temperature at this level, that will contribute maximum to the radiance measurement by satellite sounder. But if there is any change in the temperature of surface, Earth surface, or lower atmosphere, or even middle atmosphere, there will be no change in the measurement which we have done at wavelength lambda 3. It means your satellite sounder is only able to see the upper atmosphere. Okay. Now, if you come in between some wavelength here, maybe around 13.5 micrometer, then what will happen? There will be some intermediate layer. It will not be able to see surface, and it will be now not able to see the upper troposphere, but it will be able to see a middle atmosphere somewhere. We can say mid atmosphere, okay? And the weighting function at lambda 2 will be something like this. That is, your satellite sounder at lambda t is sensitive maximum to this the change in temperature in this middle atmosphere. So you have got 3 sounding channels, lambda 1, lambda 2, lambda 3, where lambda is able to sound or to make a measurement of temperature near Earth's surface. Lambda 2 is able to do temperature sounding in the middle atmosphere, and lambda 3 is able to do a temperature sounding in the upper troposphere or upper atmosphere, okay? Now, if you have a radiometer where you can have several measurements, wavelength measurement in between. So you can have several type of weighting functions here, several channels which are able to make measurement at different layers. So that way, your sounder will be able to sample different layer in the atmosphere, and that radiation, when you invert or convert into some meaningful information, that will provide you temperature of that particular layer, okay? So this is about temperature sounding from CO2, the absorption band. Now, how to do water vapor sounding? Once you have made measurement from CO2 band, you know the temperature sounding, okay, that you have done from CO2 sounding channels. Now, what will happen? You can say that now for water vapor region, when you move to water vapor absorption band, in that case, this function is now known. Your radiance function in the different atmospheric layer, that is the temperature of different atmospheric layer, is now known quantity. So the only unknown here will be tau, that is transmittance. And that transmittance is only because of change in water vapor amount, because this absorption band corresponds to absorption by only water vapor. Now, what will happen? If you are making measurement from 6 to 8 micrometer here, that is water vapor absorption band, this wavelength will be giving you water vapor information of lower atmosphere. This channel will be giving you, that is around 7 micrometer, that will be giving you information about water vapor change in middle atmosphere. And this layer, that is the peak of absorption band of water vapor, that will be giving you information about water vapor changes in the upper troposphere, okay? So, and if you have more and more channels, you can get information about water vapor in different layer in the atmosphere. Now, that is about water vapor. Now, what if you want to make measurement of ozone or any other trace gases? So in that case, what will happen? Instead of you are making measurement in this absorption band of water vapor or CO2, you will make measurement in the absorption band of ozone. Now, similar to this, you have known temperature, you have known from CO2 absorption band. So when you make measurement here, hundreds of measurement in ozone band, you will be able to get unknown quantity, and the unknown quantity tau, that is transmittance in this absorption band, is only due to changes in ozone in atmosphere. So what will happen? In that case, these 3 points will be corresponding to water vapor. This will give you water vapor information of lower atmosphere. This will give you ozone information of middle atmosphere, and this part will give you information about the upper atmosphere, how much ozone is there, okay? So this way you can go on building atmospheric sounding for various other trace gases like methane, carbon monoxide, and any other gas which you want to measure. Now, little bit about this weighting function here. So weighting function, if you want to understand why weighting functions are bell-shaped, you can quickly see this one, that lower atmosphere has strong radiation is emitted because of high atmospheric density near surface, but almost all is absorbed by the upper atmosphere. Now, if you talk about upper atmosphere, little radiation is absorbed by the further upper atmosphere, but little radiation is emitted because of low density of gases in the upper atmosphere. So what will happen? As a result, the radiation from atmosphere at an intermediate altitude has a maximum contribution. So you will have this type of bell-shaped weighting function, and depending upon strength of absorption band or absorption line, this peak of weighting function will keep on shifting. It can be from near Earth surface, lower atmosphere, middle atmosphere, upper atmosphere, and stratosphere, so on. For example, you can see here, if we talk about INSAT 3D sounders. So INSAT 3D sounder, we have 18 infrared band starting from 3.8 micrometer here. That is the channel number 1, and up to this one. Sorry, this is channel number 18, and this 14.5 or 15 micrometer. This is channel number 1. Okay. Now, if you see wetting function corresponding to all these spectral bands, you will see that this one is near surface channel, then little upper atmosphere, little upper atmosphere. This is say you can say mid troposphere, and this is upper troposphere. So these are channel number 13 to 18 CO2 absorption band here. And if you go to the second panel here, they are channel number 1, 2, 3, 4, 5. So these 5 channels are placed in CO2, carbon dioxide absorption band, and they provide you temperature information of various layers in the atmosphere. For example, this channel number 1 provide you temperature information of lower troposphere. The second, little up higher. The third one is peaking here. The fourth one is peaking somewhere here, and the fifth channel is peaking here. So you can see that these 5 channels wetting function are peaking in different layer in the atmosphere. So they are providing you temperature information broadly in the broad atmospheric layers throughout the atmosphere. Now these 3, there are only 3 this water vapor absorption bands in INSAT 3D sounder. So basically you are getting water vapor information only in 3 broad atmospheric layers. So this channel, this first channel here provides you this lower troposphere, the second channel mid troposphere, and the third channel here at the center of absorption band that provides you water vapor in the upper troposphere. So this way you can keep on building the number of wetting functions that can sample different layer in the atmosphere, and then you can get atmospheric sounding. And there are 2 things. Forward problem. So forward problem basically is actually a radiative transfer equation, where if you are given, if I give you what is temperature profile in atmosphere, what is water vapor profile, what is ozone profile, so from that you can compute what is radiance at each wavelength band received by satellite. So forward problem is very, very simple. Only thing is a forward problem is giving you spectral radiance only at one particular lambda, one particular spectral line. And because atmospheric sounder are broad band sounders, so you have to convolve those over spectral response function to find out what is the radiance received by each of the broad channels. Okay, so I'll quickly go through these. Now, what is inverse problem? So inverse problem actually is a retrieval problem. Now, once you know from a sounder, like for example, INSAT 3D sounder, you have information only on 18 absorption bands. Okay, they are absorption band due to water vapor, due to CO2, due to ozone. Okay, now from those 18 measurements, you have to find out the infinite measurements. Your observation, your unknowns are infinite. That is, the temperature is a continuous function in the atmosphere. Okay, the water vapor is also a continuous function in the atmosphere. Ozone profile also is a continuous function in the atmosphere. So unknown are infinite. So how to retrieve those infinite amount of informations from a finite number of measurements? That is called ill-posed problem. Okay, and then there is second condition, that is ill-conditioned problem. That is because apart from being a limited number of channels, even those measurements, limited number of measurements contain a certain amount of noise in the observation. So those noise further makes your life difficult, because that becomes, even your problem becomes ill-conditioned. So your inverse problem basically is ill-posed and ill-conditioned. To solve that, you have only few solutions. So first and foremost is statistical retrieval. And I understand Dr. Randhir has described this very well, so I'll quickly go through. So statistical retrieval, you would have to have a training data set. Okay, and in training data set, if you have simultaneous measurement of satellite measurement of sounding channels, as well as your atmospheric variables like temperature profile and humidity profile, ozone profile, you can build up a big this matchup data set. And from that matchup data set, you can build a statistical relationship between atmospheric sounding and sounder observed radiances and your atmospheric profiles. And then you can invert that function, that statistical function which you have derived to retrieve the temperature and humidity profile. So what are advantages? That the retrievals are actually computationally very simple. They do not need radio transfer models during retrieval, but it requires no knowledge of transmittances. Okay, the disadvantage is that a large training data set is necessary. So what will happen when a satellite is launched? So that itself, you will start building the matchup data set. So you need at least minimum 6 months of matchup data set between your radiation profile of temperature and humidity and simultaneous satellite measurement of radiances in sounder channels. So that becomes very difficult task, but there are ways to do that. That before launch itself, you can have simulated satellite observations because you have a radio transfer model and you have radiation measurements for past many years. So from that, you can prepare a diverse profile database. And from the diverse profile database, you can generate, you can simulate atmospheric, satellite radiances, and then make one statistical retrieval. Okay, so that way, the first day of the observation from satellite also, you can have one retrieval algorithm ready based on your simulations prior to satellite launch. The second and most important is physical retrieval. Now, statistical retrieval, they are very the retrieved amount, they are very smooth profile because your weighting functions are broad. So whatever statistically they are actually smooth function. So your temperature profile, humidity profile will be good, but they will not show the sharp gradients in vertical direction. So vertical resolution will be very, very poor. So what we have to do is we have to employ a physical retrieval algorithm where during each iteration, you have to make a first guess measurement and then try to adjust your first guess based on radio transfer simulations. That I will describe in a diagram here. Here, this one. So what we do in statistical retrieval, first I will describe this one, that you have a number of radiation observations over worldwide, okay, for many years. So from that, you will make use of a radio transfer model and try to generate a simultaneous data of satellite measured brightest temperature or radiance along with the vertical profile of temperature and humidity. Okay, and then based on that, you will generate one degradation coefficients for your sounder channels, and that can be used to get a statistical retrieval. The physical retrieval, what we do, you have sounder radiances in 18 channel or 1000 channel, whatever it is. Those channels you can even average, you can have single channel retrieval as well as 3x3 channel or 5x channel. That is to reduce noise in your measurement. So you can simply average, and that averaging over 3x3, 5x5 also minimizes the probability of cloud within the FOR, that is FOR of 50 kilometer, 30 kilometer, or a single pixel of 10 kilometers. Okay. Now you have to remove those pixels where there is cloud, because over cloudy regions you cannot do atmospheric sounding because infrared, they are very much limited by presence of cloud. So what you will do, you will first see whether a pixel is cloudy or clear. If it is cloudy pixel, you will reject that pixel. You will say that this is cloudy FOR, so I will not do sounding over this place. But if that pixel is clear from cloud, and then there are sufficient amount of information available within one FOR, that is about 25% of pixels are clear within FOR of 5x5 or 3x3 region, you say that, okay, this area seems to be clear, this FOR. So I will average all the radiances or brightest temperature by sounder channel within that FOR, okay, only for clear portion of the FOR. And then that average, I'll say that, okay, that is my satellite observations within that FOR. So I will convert that radiance into brightest temperature. If your retrieval algorithm, you need this brightest temperature, okay. Now this Y is my observation, satellite observed, clear sky, brightest temperature, or clear sky radiance. So this I will stop here. And then I have another part here, that is the first guess. So first guess can be model forecast. So model forecast, first guess I take because model forecast these days are very, very good. So I can take model forecast, 3-hour forecast, 6-hour forecast, or 10-hour forecast as a first guess. And from that first guess temperature, humidity profile, you compute satellite sounder radiances or brightest temperature using a radiative transfer function. This F is here, radiative transfer function, okay, the forward operator here. Now, once you have computed the first guess radiance and you have satellite measured radiance here, you compare these two. And when you compare these two, what you will do, if the difference between satellite measured radiance and first guess derived radiance is matching very closely, then you will say that, okay, my satellite measurement is consistent with your first guess. That is, the first guess itself is my true state of atmosphere. But if it is not matching, if there is large difference in any of the channel, what you will do? You will try to modify the temperature or humidity profile of that particular layer where the weighting function of that particular channel is peaking, where there is large difference. Okay. Now, by adjusting temperature or humidity profile, what you will do? You will again adjust the profile and go back to this step here, and you will again compute radiances using that adjusted profile. Okay, the first guess profile you have adjusted at xn+1. Now again you compute the radiance from that adjusted profile and again compare with your satellite measurement. At this point, again, if you find that they are matching with within a certain threshold, then you will say that, okay, now it is matching. So what is adjusted profile is your final solution, and then you will exit and say that physical retrieval is successful. But if it is not, you will continue for 3, 4, 5 or whatever predetermined number you want. You will continue with those number of iteration, and if it is not converging even after 7 or 8 this iteration, you will say that physical retrieval not possible and this physical retrieval is failed. So what you will do? You will assign regression or regression retrieval or first guess as your final retrieval. Okay, and if that you are able to minimize that error, you will say that your physical retrieval is successful, and the output profile will be your physically retrieved atmospheric profile. Now you can say that if you have a broad spectral sounder like gauge sounder where you have 18 channel, so channel number 1 gives you information about top atmosphere, channel number 2 little lower, and 3, 4, 5, 6, 7, 8. Now channel 8 is around 12 micrometer, which gives you temperature information of surface. So you can see from top to down, you are able to make a sounding of temperature at different atmospheric layer. Then there are 3 channels, this channel, this channel, this channel, for sounding of 3 water vapor channels. And then there are various other channels that are used for atmospheric sounding of temperature and water vapor both. This is an example for this insert 3D sounder. And insert 3D sounder, you can see, if you see this one channel number 1, sorry, this is 1, 2, 3, 4, 5. So channel number 1 is this one here. Okay, 1 is peaking at top of atmosphere, 2, 3, 4, 5, like that. Sorry, 1 here, 1, 2, 3, 4, 5. So channel number 1 gives you information about top of atmosphere. So this is top of atmosphere. You are not able to see anything below lower atmosphere. Okay, you are not able to see even clouds in this picture. When you move on to channel number 2, so channel number 2 is here, that is around tropopause. So you are able to see some tall clouds here, signature of some tall clouds here. When you move on to channel number 3, that is 3 channel is weighting function is around mid atmosphere 400 SPA. So in that case, you are able to see cloud which are taller cloud, high altitude clouds. But if you come down to lower and lower altitude weighting, these channels, channel number 5 and 6, you are able to see lower and lower atmosphere. And at channel number this 5 or 6, you are basically at atmospheric window. Okay, atmospheric window within 10 to 12 micrometer, and that is able to see surface features. So here you are able to even see surface features, land and ocean contrast also you can see, and you can see wherever there are clouds, low cloud or high cloud, all clouds you are able to see here. So this is giving you temperature information of different layers. And this water vapor, similarly here, if you go to these 3 channels here, so this is water vapor of upper atmosphere, lower atmosphere, water vapor of middle atmosphere, and water vapor of top atmosphere. Okay, so this way, by making measurement in different sounding channels, you can make measurement of temperature and humidity profile in different layer in the atmosphere. And from those different channels, you can retrieve temperature profile in different atmospheric layer from surface to about 50-60 kilometers, and water vapor from surface to tropopause about 15 to 20 kilometers. So this is these are the 3 channels, water vapor 3 channels that are used to derive water vapor in lower in the troposphere, and CO2 channels are used to derive temperature in the troposphere as well as stratosphere. And there are various other parameters which you can derive from atmospheric sounder. Now I will come to this hyperspectral sounding. So you know how this evolution has taken place. about 70s, we had a 19-channel sounder from NOAA satellites. That is high-resolution infrared sounder in polar orbits. There we had 19 channels, which are similar to our INSAT 3D, this geostationary sounder. Then came geostationary sounder, gauge sounder, that started around 80s. Then in 2002, around 2001 and 2002, AIRS was launched on board Aqua satellite. That was the first pseudo-operational hyperspectral sounder, having 2,378 channels. Then around 2006, EASI was launched on board this Meteorology satellite, and there you had channels, 8,000, more than 8,000 channels. That is a true hyperspectral operational satellite. Okay, and then around 2006 or 11 or 12, we had NOAA also, NOAA JPSS, Joint Polar Orbiting Satellite. So there also we had hyperspectral sounder, cross-track infrared sounder, which had actually around 1,600 channels. Now these are from multispectral sounder to hyperspectral sounder on polar orbiting satellite, and then we are now moving. Next year we are moving towards geostationary hyperspectral sounder that we will have Meteosat third generation satellite MTGS. Today we have Chinese satellite FI4 series where we already have hyperspectral sounder on geo platform, but we are waiting for Meteosat third generation that we will have the first operational sounding system available. So this I will quickly go through because time is actually less. So I will quickly go through hyperspectral sounder. So what is hyperspectral sounder? You have seen that if you have multispectral sounder, that is 6 channel in CO2 band from INSAT 3D sounder, 3 channel in water vapor channel. So you have limited amount of information. But if you have thousands of information available from this hyperspectral sounder, I had one animation that I can show at the end if time permits. So here you can see that from thousands of channels in hyperspectral sounder, in contrast to 3 or 4 channels in your multispectral sounder like INSAT 3D, you can have thousands of weighting functions. So each weighting function is sampling different atmospheric level. So you have information about every atmospheric level from surface to about 10-15 kilometers. And each layer, that each this spectral channel is sampling different layer in the atmosphere. So each layer in the atmosphere is being sampled. So this way, your hyperspectral sounder provides you very high vertical resolution information. Now, I will quickly go to some of the examples of hyperspectral sounder. If you have multispectral sounder like INSAT 3D or GOES or HERS, that is high resolution infrared sounder, your spectra is like something like this, average spectra. But if you go to hyperspectral sounder like AIRS and CRIS, and then finally EASI, where your spectral resolution is very, very high, you are able to measure every absorption lines due to oxygen, carbon dioxide, water vapor, methane, or any other gases. So when you are able to measure radiation emitted at each of the spectral line, you get very pure emitted spectra due to various gases from different level in the atmosphere, and that information gives you very high vertical resolution. And also, like in this one, if you have multispectral sounder, your CO2 measurement can be affected by water vapor and can be affected by ozone. So that will provide some impurity in your absorption spectra. But in hyperspectral the sounding, your spectra is pure. You know that which spectral line is by CO2, which spectral line is because of water vapor, and which spectral line is because of methane. So that way, you can accurately do atmospheric sounding of temperature as well as various trace gases, ozone, methane, or any other gas. Now, this anyway, I have shown this one example of that. So time is less, so I will quickly go through this one. So what is the most important feature of difference in multispectral and hyperspectral sounder? So if you try to see information content, how much information is contained? See, if we are having 3 or 6 channel in multispectral sounder, and when we go from there, when we go to thousands of 2,000 channel or 8,000 channel in hyperspectral sounder, we cannot say that our information has increased by 1,000 because they are all overlapping weighting functions. So overlapping of various channels, they will reduce the amount of independent information. So you can see, if you see here, a multispectral sounder will have about 3 to 4 independent piece of information from temperature, and about 2 to 3 independent piece of information for water vapor. Okay. But if you go to hyperspectral sounder, your information content for temperature profile increases to 14 and water vapor it increases to 8, and which is very close to the information content which you get from radio sound measurements. So you can see here your hyperspectral sounding measurements, they become very close to your observed radio sound this measurements. And one example you can see here, very much important, this one, because when you convert this into this brightest sounder observation into temperature profile or humidity profile, you want to see what type of accuracy you are able to achieve. So when you move from this multispectral sounder to hyperspectral sounder, this one, you can see accuracy of temperature retrieval and accuracy of water vapor retrieval. So top panel shows the accuracy of temperature retrieval has improved from about 1.5 to 2 or 2.5 K in multispectral sounder. It has improved to almost 0.5 K to 0.6 K throughout the atmosphere in case of hyperspectral sounder. So different level of resolution keeps on, but after a certain time, there is no drastic jump in improvement. So it's not advisable that we go further down. We can go on reducing the spectral resolution. So we can arrive at a certain level, 0.5 to 1 centimeter inverse, which we can say is good enough to give us accurate atmospheric sounding. Similarly, water vapor, you can see what multispectral sounder was giving about 25 to 30% accuracy in water vapor throughout the atmosphere. From hyperspectral sounder, you are now able to get about 10 to 15% of accuracy, which has actually improved your capability of numerical weather prediction models these days. That's why our this forecast has become very, very good. And you can see this example here. The amount of data which is going into an NWB model from hyperspectral sounding now, it's almost every 6 hours you get one coverage over a particular region. This is ERC METOP satellite. So METOP, the ascending or descending time is 9:30 a.m. and 9:30 p.m. For polar routing satellite, NOAA satellites, it's about 1:30 a.m. to 1:30 p.m. So these two space agencies, EUMETSAT and American, they have shared the orbital time so that they can get every 6 hours you can get hyperspectral sounding over entire globe, and that has improved our this numerical weather prediction capability tremendous way. Now there are various examples. I will only give you example of one of the hyperspectral sounder, that is ERC. And by that you can understand what are the capability of hyperspectral sounder. So this METOP A, B, C were launched in 2006, 12, and 18. Now currently we have even METOP C operational, and the resolution of ERC hyperspectral sounder is about 15 kilometer. But within each 15 kilometer, you have a high resolution coverage from AVHRR or HERS, and you have coarse resolution AMSU A and AMSU B, that is microwave sounder. So based on combined infrared and microwave sounder, you can get clear sky sounding over entire globe. And because infrared sounding, whenever there is cloud, infrared cannot do sounding, but at the same time you have microwave sounder available, because microwave sounder can see through cloud because it's not getting affected by cloud. So if you are making measurement in microwave sounder and infrared sounder simultaneously, you can get measurement of atmospheric profile throughout the world. Most of them, 70 to 75% of the Earth is covered. Only certain cases where there is high dominance of water vapor or rain, over those places you may not be able to get sounding. So what are those parameters which you get from hyperspectral sounder? You get temperature profile, humidity profile, surface temperature, and surface emissivity. They are basically for each IFOV, that is about 50 kilometer. Then accuracy you can see here, about 1K for temperature, 10% for humidity, 15% for ozone, 10% for cloud cover. Then there are various other gases: fractional cloud cover, cloud top temperature, cloud top height, cloud phase, column integrated ozone, and then total column N2O, total column CO, methane, carbon dioxide. So apart from temperature and humidity profile, you also get information on cloud properties, and you also get information on various trace gases. Okay, and one example you can see here. This is EUMETcast, which we receive from which we get IMD or NCMR level of New Delhi, and even we also have that operation at SAT. So every day we can receive EUMETcast data in real time, and if you see, this much coverage is there from ERC for temperature as well as humidity. And these are the example of various other trace gases. Now, JPSS, apart from METOP, then JPSS is contributing in another orbit. This also very similar to METOP series of satellite, where ERC is replaced by this CRIS, the cross-track infrared sounder. We also have high-resolution imager, and then we also have advanced technology microwave sounder. This is microwave sounder. So by combining microwave sounder with hyperspectral infrared sounder, we are able to get clear and cloudy sky atmospheric sounding. So you see here, JPSS also has ensured the continuity of hyperspectral sounder till 2035, 2040. Okay, so these two satellite series will be there for next 15 years also in orbit, and in future we will also contribute from our Indian missions in the hyperspectral sounding or microwave sounding. So quickly going through this hyperspectral sounder applications. So these are the four, five categories here. That is input for weather prediction model, local severe storm, aviation and marine forecast, climate change research, input for air pollution model, satellite intercalibration, and characterization of thermodynamical and wind profiles. So you can see here, if you see the numerical weather prediction, actual improvement in numerical weather prediction model forecast happened only after launch of these hyperspectral sounders. And now you can see the impact of hyperspectral sounder is very, very large. This is ATOPS, the ERC, this is ATMS, this is CRIS. So the impact of these hyperspectral sounder is very, very large. This is work done by our own colleagues at Ahmedabad Center. And you can see the impact of hyperspectral sounder is much, much higher than any other instrument. The other application is nowcasting. Now, nowcasting, the sounding is very, very important, because if there is a cloud formation, after the cloud has formed, you can keep on tracking the development of cloud in horizontal as well as vertical direction. Okay, its growth in vertical as well as in horizontal. So you can say that, okay, now there is a possibility of thunderstorm development. But prior to that, you have no signature here in this part, So sounder can provide you that information before initiation of a thunderstorm or a convective event in terms of atmospheric stability. So if you have those informations at this point, you can get the information whether this area there is any likelihood of a convective storm or thunderstorm. So you can see this is one typical example of the convective storm here. And if you see this one, if one storm, you can see this place, this is one typical example taken from literature by Tim Smith. And you can see this place, there was a thunderstorm at this point, about 18 GMT. Before that, the TPW at that point increased drastically, and lifted index decreased drastically. It becomes highly negative. So there was a buildup of water vapor at this point. At the same time, atmosphere was also becoming highly unstable. Lifted index negative means atmosphere is very, very unstable. So that gives you information that there is something happening at that point, because TPW is continuously increasing, and lifted index is also increasing towards a negative direction. So this point we can predict that there is a likelihood of thunderstorm development at this point. So your imager can pick only after 18 GMT when cloud formation has taken place, but sounder can give you increased predictability of thunderstorm by almost 3 to 6 hours, and that is very, very important time for prediction of thunderstorm events. Then other applications, you can see temperature inversion. If you have broad spectral sounder, you cannot get inversion very accurately. But if you have sounder, which can give you information of temperature profile in a very high vertical resolution, you can get you can also get temperature inversion information, and that also can give you predictability for this type of phenomena, that is fog. So before fog initiation, if you see that wind conditions are calm and there is a strong temperature inversion in the lower atmosphere, there is a possibility of fog formation. So this can also be very important input for your nowcasting of fog. And then there are various other non-traditional application of hyperspectral sounder. That is, because I have already told you that this can also be used to measure the trace gases, various trace gases, and this list is very long here. Some are operational product, some are research product, and some are just test products here. So you can see the hyperspectral sounder, they have information for each of the gases. There is the absorption features or absorption lines due to many gases: hydrogen sulfide, formic acid, nitrous oxide, hydrogen cyanide, furan, acetylene, and so on. It means if there is abundant amount of these trace gases in atmosphere, you can get that, or you can pick that signature in your satellite hyperspectral observation, and that can be monitored. Okay, for one example here you can see, because during volcanic eruptions, many of these trace gases are ejected in atmosphere. So you can get that signature clearly from hyperspectral sounder. So many of these gases and their movement around the globe is picked up very nicely by hyperspectral sounder, and that is one of the very big example for or application for air pollution monitoring. Similarly, for climate change also you can use, because you get very high accuracy of temperature profile, humidity profile. So you can measure the trend. If you have long-term data, you can measure the trend over various atmospheric layer, like decreasing trend of temperature in the stratosphere and increasing trend of temperature in the lower atmosphere. That is the part. That is the the phenomena that is taking place due to global warming. And then there are dust storm tracking. And more importantly, you can also get surface features, because the first slide, when I showed you first few slides, that each spectra, each wavelength will have different emissivity spectra. So by measuring the complete spectra in hyperspectral sounder, and you know that the spectral signature is different for seawater, for ice, for oak tree, for soil, for sand. So you can get spectral emissivity also from hyperspectral measurement. So surface type information also you can retrieve. Now, one very interesting thing will happen when next year, when we have this hyperspectral sounder in orbit from Meteosat third generation. And that what will happen even before cyclone formation. One of the most important parameter is wind shear. Now, so far, wind shear is very difficult to get from over a clear sky, because there are no water vapor or there are no cloud tracers available. So cloud motion vectors cannot pick those type of those type of features. But if you have high hyperspectral measurement in water vapor in absorption bands, you can get water vapor in various atmospheric layers, and by tracking those water vapor motions in various atmospheric layers, you can generate wind profile in vertical and with a very fine vertical resolution. So that can provide you information on wind shear, and which will be very, very important for cyclone monitoring and cyclone prediction in advance, or cyclogenesis. So that will happen sometime next year. And this is summary that IR and microwave sounders, they provide vertical distribution of temperature, water vapor, and other trace gases in the atmosphere. Hyperspectral IR observations provide higher vertical resolution and high accuracy of temperature and water vapor sounding, apart from providing information on various greenhouse gases. Presently, we have EARS, EASI, and CRIS hyperspectral sounder in low Earth orbiting, polar orbiting satellites. But in future, we will have geostationary hyperspectral sounders, for example, MTG next year. And these hyperspectral sounder will improve medium range weather forecasting and provide important information on climate monitoring. And more importantly, an advanced geostationary hyperspectral sounder will provide enhanced temporal sampling to improve the nowcasting and shorter range prediction. Okay, so if you want to continuous monitor the TPW or lifted index at one particular place, you need to have very good temporal sampling, and that can come only from hyperspectral sounder on board a geostationary satellite. So this ends my presentation here. So I think I have taken more time, but we can take any number of questions you have. Okay, but
thank you, sir.
I would like
for delivering the talk. I think now we'll have a question and answer session. I request Dr. Divya Prakash and Swagata.
But before that
group photo, right? Yeah. So now I request all the panelists to turn on their videos so that we can have a group photo. Thank you. Sir, can you unshare the presentation, sir?
Yeah, I'm doing that, yeah.
Yes. Thank you. Divya is taking? Swagat?
Mohan is expert on it.
Yes, I am taking, sir, but Bhatia sir's video is switched off.
Yeah.
Sir, yeah, ready. Yes, sir. Thank you all.
Okay, thank you, Dr. Mohan. So now I request Dr. Divya Prakash Swagata to take over this question and answer session.
Yeah, Divya, you start.
Thank you. Thank you, lecturers. Sir, wait a minute.
So let's. So Divya, if you are okay, otherwise I can start.
Yeah, I am.
I can also read those questions from question and answer. Is that okay?
Yeah.
Okay. So
Yes,
there
sir.
are questions. Maybe first question is by Swadhin Satapati. What is the basic difference between the imager and sounder payload in terms of acquisition of images? Why imager has high spatial and temporal resolution than a sounder? Okay, good question. Actually, imager basically is an instrument where we want to make measurement of surface. The surface can be either Earth surface or it can be cloud surface. Okay, so if you want to make measurement of cloud properties, or if you want to make an observation of surface, sea surface temperature, length features, okay, in that case we want to resolve it very high spatial resolution. Okay, so what we'll do, we will have this microwave imager channels working basically in you can say a window region. If you want to make measurement on cloud, you make measurement in the infrared window 10 to 12 micrometer. If you want to make measurement of sea surface temperature, that also will be window region, but we split it to get the difference, to get the correction for water vapor in two channels. Okay. Now, if you want to make cloud, if there is cloud, so this window channel will give you information about cloud top. Okay. So if you have more number of channels like visible channel, sphere channel, near infrared channel, or MIR channel, in addition to getting information of cloud top temperature, cloud top pressure, you will also get information about cloud properties like cloud microphysics. Okay, so that is the application you want to get from imager channels. And imager channels mostly, I said that they work in the window channel, and they should have very high this spatial resolution to make that measurement. Like if you want to make measurement of cloud motion vector, so you have to observe cloud features, small cloud features, which will be moving from one place to another place and within half an hour or next half an hour, 2 hours. Okay, so your spatial resolution becomes very, very important. Now, when you want to go for atmospheric sounding, now sounding is just opposite to imager. In imager, you want to get information about the surface. So you make measure in the window channels, either it is visible window or infrared window. Now, sounding, you want to get information about atmospheric layer. So that will be possible only when you make measurement in the absorption band. Now, when you are making observation in absorption band, the gas which is absorbing also emits its own radiation, because absorptivity equal to emissivity at one particular wavelength. So that way we can go on building number of channels where absorption strength is different, and that way we will be able to get radiation from different layer in the atmosphere. Now, what happens when we are talking about sounding? Because the emitted energy is very, very small, you are only measuring the energy from one absorption band. Okay, so in that absorption band, because energy emitted is less, so you have to make this resolution, spectral resolution, this is little coarser, or you have to make the spatial resolution little coarser. So you have the two choices. So that is why to get sufficient sensitivity in your sounding observations, you either degrade your spectral resolution or you degrade your spatial resolution. Now, hyperspectral sounder, the this application is improved spectral resolution. So there you cannot compromise on spectral resolution. So what do? You degrade your spatial resolution. So spatial resolution of most of the hyperspectral sounder right now is 15 kilometers. Okay, so that is the main difference which I can answer from this first question. And one
Sir, I will read the question, rest of the questions.
Okay.
There's another question from Swadhin. Can we retrieve trace gas profiles from INSAT 3DR sounder?
Okay, so INSAT 3D sounder, because for trace gas, now water vapor anyway we are retrieving from 3 channels. So that we cannot say trace gas, that is one dominant gas in atmosphere. Now ozone, so ozone there is only one channel. So retrieving ozone profile from one channel becomes very, very difficult. But still, using physical retrieval, we know that what is the weighting function of your ozone channel. Okay, so based on that, whenever the wetting function changes in atmosphere up and down, based on that we can modify a first gas profile of ozone. So yes, we can, but that we are doing on an experimental basis because we have only one ozone channel. So to derive basically this ozone profile, we need many number of channels where wetting function will be peaking at different layer in the atmosphere. That happens only in hyperspectral sounder.
Okay, so next question, Neeraj. So he's asking for suggesting books for the atmospheric sounding in IR as well as in microwave region. Can you suggest a few books?
Actually, there is one very good by Kidder and Wanderhaar for satellite meteorology. So that covers all the aspects, including your sounding. Okay, so that is very good book that you can follow.
One question from Shubhendu Karmakar. Sir, can we say hyperspectral sounding is optimal in contrast to radio sound observations, considering day-to-day operation cost?
Especially, I want to mention this is question from IMD.
Okay. Yeah, actually, yes. When you see from day-to-day operations, radio sound, how many radio sounds you can operate and how much will the cost? But if you have hyperspectral sounder, the quality of sounding is very, very good. Even one radio sound is sometime you say that okay, this may be representing a 50 by 50 kilometer because radio sound also drifts when it goes in vertical. So you can say that okay, this is giving you lower atmosphere, it will be very high spatial resolution, but upper atmosphere it will be drifting somewhere else. But you can say that hyperspectral sounder, that is giving you optimal sounding, and more importantly, equally good over entire globe, over ocean. In fact, the quality is much better. Sounding, always over land or mountain region, the quality will degrade a little bit because spectral emissivity also coming into picture, where that is highly variable. Over ocean, it is almost a constant or a background. So sounding over ocean becomes very, very good. And that is another example, that is another advantage for atmospheric sounding. So that's why, before 2002 or 2004, when there were no hyperspectral sounder, your forecasts were not good. Your forecast of temperature and humidity were almost, temperature forecast accuracy was 1 to 2K, 1.5K above that. And humidity sounding was, humidity forecast was 20% to 30%. But only after you have METOP series and JPSS series of hyperspectral sounding, that your NWP forecast of temperature itself has improved. And that forecast temperature and humidity is now matching very close to your sounder, even your ground-based sounder. Okay.
Thank you, sir. There is one question from Satish Vijayaragavalu Haridas. It was mentioned in one of the slides that hyperspectral can provide wind profiles. Is this vertical profile of wind, or is it over land or ocean? And how we can obtain this vertical profile?
Okay. So yeah, that's a good question. Actually, this will happen only from, see, I will just give one example of insert imager or imager channel. Okay, insert imager or gauge imager, any of the geostationary imager. Now, geostationary imager has capability to provide you image every half an hour. Now, if you have water vapor imagery, you know that from cloud motion vector, by tracking cloud motion, you can get cloud motion wind. But that is only where you have presence of cloud. When there are no clouds, even atmosphere will have water vapor everywhere in atmospheric layers. So water vapor imager channel in INSAT 3D or any other geostationary satellite, that provides you water vapor wind over upper troposphere, that you know very well. Okay. Now, if you have hyperspectral sounder where you are having water vapor information of various layers, from a weak absorbing channel will give you water vapor information of lower atmosphere. From very strong absorbing channel will give you water vapor information of top layer, and so on. The entire vertical profile of water vapor is available. Now, if you have every half an hour geostationary this imagery or sounding available, you can derive that water vapor motion vector or water vapor wind at each of the layer, corresponding to each of the sounding layer. Okay, so that way you are able to generate the vertical wind. It's not vertical wind, but it's horizontal wind, and at different atmospheric levels. And that, that's what I explained, that is very important for wind shear information when you are talking about cyclogenesis.
Thank you, sir. There is one question from Manikyal Rao Tankala, IMD. what are the future applications of hyperspectral soundings with respect to atmospheric parameter measurements?
Yeah, so the future applications actually is first application which I'm talking about is nowcasting. Right now, nowcasting is not one of the applications because a hyperspectral sounder will come only after 6 hours, 12 hours at one place. Okay. Now, like inside 3D sounder, we have every 1 hour sounding, but the quality is not that good because our spatial resolution is not good, vertical resolution is not good. But when we have hyperspectral sounder on geostationary platform, you will be able to get atmospheric stability, atmospheric profile of water vapor, high quality information every 15-minute or every 30-minute interval. So that will give you very good information for nowcasting at every location. Okay, irrespective of because it is fixed over a particular region, so you will be getting continuous information on lifted decks and the buildup of water vapor. So that is one of the most important application, that is for thunderstorm and this nowcasting applications. Another application will be once you improve your noise NEDT, noise in your different channels, you will be able to get trace gases, various trace gases, which you have seen that during volcanic eruptions you can get information about so many trace gases. But because they are ejected in atmosphere in a large amount. But future we can have very high sensitivity for each of the channel, a small amount of noise that will make this observation of various trace gases possible from hyperspectral sounder. So air quality monitoring and those applications will be one more important thing we can add in that.
Thank you, sir. There is one question from Piyush Gupta. He's asking if he wants to use NWP model by using this satellite data, and how many number of channels minimum required to run the NWP model.
Okay, yeah. So actually, per hyperspectral sounder, you have seen that there are thousands of channels, but many of the channels you must have seen they give redundant information. There will be 100 CO2 gases, CO2 the channel where you will have this that the wetting function is almost one same channel, if similar to water vapor. So assimilating this redundant amount of information will become very difficult, and it will be time consuming also. So what you have to do is you have to find out optimum number of channels which has the information content very close to your entire spectra. Like we have seen that if you have about 50 channels or 200 channels, so that those 200 channels will contain the very similar amount of information content that is contained in 8500 channel of ERC. So you can try to minimize. You can try to have 200 or 300 this spectral channel having independent information. So you have to first see that those different channels which you are choosing, they are independent. They are not correlated, well correlated. Another thing here nowadays is very important is assimilating principal components. Now, principal components is another way of getting independent informations. So by that way, you can even minimize. You can say that, okay, 30 to 50 principal components are sufficient to represent entire spectra. You can generate entire hyperspectral spectra from 50 principal components. So assimilation of even principal component domain also becoming a new emerging field in that. So that also will be less time consuming. And when you are talking about principal component assimilation, you are also reducing the noise. You are also going to filter out the unnecessary noise that is there in your spectra. Okay. Thank you,
sir. There is a question from Aditya. What are the typical error in the measurement of isotopic ratios of water vapors getting from the satellite observations?
Okay, yeah, this is a good question, but unfortunately, I do not have exact answer because that depends upon the amount of. That's why I said that if it is isotopic water vapor, so the amount, if amount is good enough, that depends how what is the amount of that isotopic water vapor in atmosphere that can be predicted. But I encourage all of you to look into that. To look into the spectra of water vapor, and particularly where you have those heavy water, these isotopes, whether you can find those spectra.
Yeah, the last question is, sir, what are the limitations of sounder-derived stability indices, such as CAPE and CIN?
Actually, limitations, the CAPE, CIN, those limitation will be whatever limitation we have for temperature and humidity profile. Because CAPE, CIN, lifted index, they are all derived parameters from temperature and humidity profile. Now, the limitation is only one thing, that 15 kilometer, this hyperspectral sounder has a footprint of 15 kilometers. Now, the 15 kilometer probability of finding a clear pixel is very, very small. You will have a small infringement of cloud over 1 or 2 set pixels. So that creates little problem. Okay, so the limitation is only coming from the presence of cloud. If you in future, if you have very high spatial resolution from hyperspectral sounder, maybe of the order of 1 kilometer or 2 kilometer, then even that limitation will not be there, and you will be able to measure temperature, humidity profile very accurately, as well as the derived products such as CAPE, SAIN, or this lift index. So that is the only limitation there.
Thank you, sir. One question from Rohit Chakravarti. How is this lift index retrieved from the temperature channels?
Actually, temperature channel, this lift index is basically the temperature information at surface and 500 millibar or 600 millibar. Meteorologists can answer that better way. So the how temperature and water vapor, that is both the things. So if you have information of temperature and dew point temperature, so from that you can compute the parcel. If a parcel is taken from dry derivatively is taken from suppose 600 500 millibar to surface, what is the difference? Okay, so if atmosphere is highly unstable, that temperature difference is very large. If it is stable, that difference will be less.
Lakshmi, I think we need to
stop. One more question, Swagata, last. So okay. Is there any website for the source of this hyperspectral data?
Yes. Actually, all these data are freely available to global community. You can just go to EUMETSAT website, www.eumetsat.int, and there you can go to the archival. Okay, so you can register in that website, their website, and you can select and order any amount of data. The second very important thing which I just now told, that most of these operational agencies like IMD or NCMR developed, they have EUMETCAST system there. So all the satellite data, whatever GRIS, ATMS or ERC, all data is they are getting real time at their server. So you can also have arrangement, because nowadays there is this knowledge sharing between various agencies. So you can also access those data from IMD and NCMR developed. So if you want to have in near real time, you can have some arrangement with these operational agencies to get the data in near real time. Otherwise, you can go to NOAA's website, you can go to EUMETSAT website, register there, and then you can order and download the data. But that will not be in near real time.
Thank you, sir. Sir, can I ask one question, sir?
Yeah, sure.
Sorry, it's a very blind question. I wanted to know. Because we have these measurements of rainfall from satellites as well as the radars. So we know that we compare the satellite measurements with the ground gauge measurements basically. So when we are comparing with the radar estimated precipitation, what are the limitations we'll have to take into account before this comparison?
Actually, the first radar, you're talking about ground-based radar or satellite? Ground-based radar.
Yeah, ground-based radar, yes.
Okay. The satellite measurement actually the best if you have insect type of if you are talking about rainfall retrieval from IR, water vapor or IR channels, that they are mostly based on cloud top temperature. So far, if you have ability to measure the cloud microphysical properties, cloud droplet size, cloud droplet distribution within cloud, then you can if you have a precipitation radar on board satellite, that can interact directly with the raindrop within cloud system. Okay, but if you are talking about this ground-based this rainfall which you are getting on ground, that is instant. You know that sometime within 1 kilometer also several places are there where you will have rain, and several places there are no rain. So the most important thing is very highly spatial and temporal variability of rainfall. That becomes very big problem for comparing comparing this ground-based as well as satellite-based measurements. Okay. So always I am telling you that this satellite radar-based measurements are always better than IR-based measurement. But IR-based measurement, because they are simultaneously, you can have over many period. But if you suppose make composite over several days or several hours, then even satellite-derived products, IR-based products also can give you fairly good accuracy. So rainfall is one parameter where there are various type of applications. For nowcasting or for flash flood, you want very high estimate of rainfall. That can come from from advanced imager as well as microwave or this active sensors. If you want climatological rainfall information, then you have to rely on like Ergin type of information that you every 3 hours or every half an hour you have infrared imagery. Then you try to find out quantitative precipitation estimate, average that over 1 week or 1 month. So that average sense for climate information, that information is very good. But if you want to go for application in for nowcasting, severe weather type of thing, then you have to rely on radars. Okay. I don't know. You said it was a blind question, but it seems it may be equally blind for me also to answer that question.
Yes, sir. Thank you, sir. With this, I think we are closing this question and answer session. I think we have come to the last item of this today's agenda. Now I request Dr. Mohan Kumar Das, Executive Director, Naomi, Bangladesh, also Joint Secretary for Southeasian Metal Association, to deliver vote of thanks for today's talk. Over to you, Mohan.
Thank you, Professor Lakshmiji, and of course, everyone. So, good evening, everyone. I am delighted to extend a heartfelt thank you for joining us on this special occasion, the 8th lecture of our Satellite Weekly Online Lecture Series. Today, we had the privilege of exploring atmospheric, air, and microbe sounding products from satellite, with a focus on state-of-the-art hyperspectral sounding, presented by the distinguished scientist, Dr. Pradeep Thapliyal from ISRO, Ahmedabad, India. First and foremost, our warmest congratulations and deep appreciation go to our today's distinguished speaker, Dr. Thapliyal. His presentation was not only informative, but also truly inspiring. Dr. Thapliyal's extensive knowledge about atmospheric sounding enriched our understanding, and we are profoundly grateful for his dedication to sharing his expertise with us. We would like to express our gratitude to esteemed SAMA Executive Coordination Team members, Professor Dr. T.V. Lakshmi Kumar, Dr. Akhilesh Kumar Mishra, Dr. Rohini Bhawar, and Dr. Dibya Prakash for their outstanding efforts in guiding the session, introducing the speaker, and facilitating the important question-answer sessions. Their contribution created an engaging and enriching learning experience. We also want to thank all the participants and attendees from around the world for adding diversity and depth to our discussion, making this program a resounding success. In closing, our deepest appreciation goes to the key figures who made the Satellite Weekly Lecture Series possible, especially Air Vice Marshal Retired Professor Dr. Ajit Tyagi, Chairman of SAMA, Professor Dr. Someshwar Das, General Secretary of SAMA, and Professor Dr. Shahagata Paida, Treasurer of SAMA, and B.A.T. Mishra. Their guidance and support have been instrumental in our journey. As we bid farewell, let's look forward to more captivating lectures in the future, upcoming week, as we continue to explore the fascinating world of satellite meteorology together. Thank you, and may you all have a splendid day ahead. Thank you all.
Yeah,
Thank you, Dr. Mohan. I also thank the participants as well as the panelists for attending this talk, and I also thank the participants. So, dear participants, we will be meeting next week as usual for the next talk of the lecture series. I think over to you, over to convener Swagata, program convener, final.
Yeah, I think it's a wonderful talk because 2 hours it has passed like just a few moments. So I felt really great because I also teach the same basic things in the class, and maybe your presentation will help me a lot. And I noticed Akhilesh raised his hand, wanted to say something. Okay, no. So let's before completing the things, usually I need 1 or 2 words from Professor Someshwar Das and also Tyagi sir. So please conclude.
Okay, thank you so much, Dr. Tyagi. I can see that the Director General of DMH Myanmar is present. I hope he is there. I can see him.
Yeah, he's there. He's there, sir. Yes.
And he has been attending all the lectures so regularly, being so much senior, and still he is able to spare his time to attend the lectures. We really like to appreciate him so much and request him to say a few words. Dr. Kyamo, please.
Thank you, Professor Sanshawa. Firstly, I would like to be sincerely thanks for the Dr. Pradeep Thapliyal. Today, your lecture is very interesting and very informative of all of the participants. This lecture is very useful for our operational focusing in our work. I also would like to be thanks of the Professor Ajit for the providing of this lecture series. This lecture series is the very important of the study relation of in our region. Thank you very much.
Before completing one thing, I just want to share with Dr. Thapliyal. Right now, Divya actually shared the number of participants. It is 251 participants from 24 countries. Today, yeah, it has happened.
Thank you.
Very good, very good.
Great, wonderful.
Thank you for your patience hearing. I'm always available for any question through email. So whenever a participant has, because there's so many things to cover, sometimes I have many topics to cover, so I sometimes quickly rush through my slides. Any slide or any question if you have, we are always welcome to communicate through my email address provided. You can provide my email address to all, and you are always welcome to ask any question.
Thanks a lot.
Thank you very much. In fact, it was a very interesting talk, Dr. Thapliyal, and so much of applications of satellite data in NWP, numerical weather prediction and data simulation, and you have explained them so clearly. I can see that people are appreciating, even those people who joined your, I think, lectures at SAC directly in those training courses from other countries, they are also appreciating your lectures. So thank you so much for very interesting lecture. And I think you have one more lecture later on, is it? In this lecture series, or only one lecture you have? I'm not quite sure. But the next lecture was supposed to be Dr. Baby Simon, but he has exchanged his lecture later on. And so the next, for 25th of November. Yeah, so the next three lectures will be by Dr. Asim Kumar Mitra from IMD. And after his lecture, Dr. Baby Simon's lecture will be held. So that's the small thing which I thought to share with you. And that's all from my side. Thank you once again. And I think Dr. Tyagi would like to have the final words. Tyagi, you are there?
Yeah. Once again, thanks to Dr. Thapliyal for his very, very informative and insightful talk on a topic which was so relevant. It has got so much promise to offer to the researchers as well as for the operational people to use the satellite data